And yeah, thank you, Bran, for that. Yeah, so today Patricia will be presenting what she's been doing or she's been working on for the comprehensive exam, which she'll be presenting on, is it next week?
Yeah, next Monday.
Yeah, next Monday. So she's going to run us through for 25 minutes. Then at the end, we are going to give her feedback and some questions. Yeah, I'll let her talk about the background before she starts presenting. So Patricia, go ahead, take it away.
Okay. Hi, everyone. Good afternoon. My name is Patricia Azike. So I'm a student in the Computing PhD program with emphasis on computational math, science, and engineering. Do I have to say anything again about my background?
Yeah, I think it's okay.
Okay.
Yeah.
So can I start now?
Yeah, sure, you can.
Okay. So I'll be making a presentation today on my comprehensive exam synthesis, which is on smoke models and applications. My advisors are Professors Donna Calhoun and Jody May. What is happening? Okay, this is an overview of what I'll be taking us through. So we have the introduction, the concept of smoke, my seed papers. We'll be looking at some smoke models like the box, plume, puff, particle, and Eulerian models. We'll also be looking at two smoke modeling frameworks, which are BlueSky and the National Air Quality Forecast Capability System. We'll look at some research gaps and future work, as well as some references. I'm sorry, I'm having an issue trying to scroll. Okay, can everyone see this now?
Yeah, we can see them.
Okay, so ever since I arrived in the United States, one common subject I've noticed that people won't stop talking about is the weather. People often talk about how sunny it is, how cold it is. And if I remember, about 2 to 3 weeks ago, we got an email from the Public Health Safety Department talking about how air levels was going to be reduced and people should take care of themselves. And I can remember, like, for 2 to 3 days when I went to the hospital, the nursing practitioner was just telling me how it was really bad and brown outside. Sometimes we want to sit back and understand where the smoke is coming from, especially when we can't see the wildfires. Wildfires are unexpected fires that start in rural urban regions and it can last for a long period of time and over a vast area of land. They're a common natural occurrence in several parts of the world, like in Siberia, Australia, in France, as well as in the United States. In the US, particularly in the West, California is known for its wildfires, with the largest fire since 1932 being the August complex fire of 2020. It is recorded to have burned over 1 million acres of land. And while natural occurrences like lightning are responsible for wildfires, some human activities such as land use, arson, as well as carelessness have contributed to increasing wildfires in recent years. Wildfires emit smoke, which contains harmful pollutants like carbon dioxide, carbon monoxide, methane, as well as volcanic organic compounds and particulate matter. Of all wildfire emissions, researchers are mostly concerned with particulate matter, especially the one with aerodynamic diameters of 2.5 micrometers. Because of how tiny it is, it can easily flow into the respiratory and circulatory system, causing cardiovascular mobility, neonatal defects, as well as death in sensitive groups. So this is an image showing wildfire smoke in Los Angeles National Forest, California. We can see there's lots of smoke and the effects are really devastating, to say the least. Talking about smoke, we have to understand that because of the chemical complexity of wildfire smoke, it greatly differs from common industrial pollution, and several studies are underway to assess it. The effects of smoke vary over temporal and spatial scales. That is, the effect of smoke in Idaho could be different from the effects in California. And because of this, several models have been designed to simulate its past and present behavior, as well as predict its future impact and make smoke regulatory decisions. Because of how complex smoke is, some of these models include one or more of the underlying physics governing smoke, such as the emission source stem, plume rise, the amount of heat being released into the atmosphere, the effect of wind and topography, as well as particulate matter concentration. Some other models go further to include the chemical changes that take place when smoke is released into the atmosphere, such as the interaction with the ozone layer. Though emission source stem is a significant factor to consider in modeling smoke, as it can determine whether we'll get very good or bad estimates. It is simply any forcing that causes smoke to be injected into the atmosphere. Despite how important it is really difficult to characterize the emission source stem. So researchers are often have to make certain assumptions which lead to the simplification of the model. And as they make these assumptions, errors and uncertainties increase, which are then propagated throughout the entire modeling process, giving even worse estimates. So these are the seed papers I went through. I had 4 papers. The first is really a review on smoke models for wildfires. And the second is the analysis of BlueSky Gateway, which is a smoke modeling framework. So the predictions using 2007 and 2008 California fires. The third was evaluating the smoke detecting capabilities of the National Air Quality Forecast Capability System. And the fourth paper was on ash 3D. So it's a finite volume method for simulating ash and tephra deposition from volcanic eruptions. And while we might argue that wildfire and volcanic eruptions are different, the transport mechanism for tephra and smoke are really the same. We'll be talking about smoke models now. And then the development of smoke models have seen lots of changes over the years as each successive model tries to update the features of the model before it. However, this is not always the case, as we shall see shortly. So I'll be describing the models in order of complexity from the very simple ones to the more complex ones that rely on little assumptions. The first is the box model, and according to Letao, it's the most basic method for forecasting emission concentrations in an airshed, that is the volume of air in a given geographical region. According to him, a simple box can represent an airshed in such a way that the height of the box is defined by the mixing height, and then the horizontal extent of the box is defined by the spatial area of the airshed. The source stem is considered to be at the bottom of the box. The box model posits that pollutants are instantly and uniformly spread throughout the box. This assumption leads to an oversimplification of the model as it does not account for plume rise and diffusion, making the model to be unrealistic. The box model also does not cover fine temporal scales. In order for one to get really fine time scales, one will have to divide the box into much smaller boxes. This is a computationally intensive process, and it goes against the simplicity of the model, which is its strong advantage. Despite this, it has been used to predict short and long thermal and PM changes in small and big cities. It has also been applied to predict ground level concentrations. However, it overestimated the concentrations that were within 100 kilometers of the fire because of the assumption that the pollutants are instantly and uniformly spread. The box model has also been applied in the ventilated valley box model, which is the VAL box model, in order to estimate concentrations of particulate matter within a valley. However, this model met really strong negative reviews from the United States Environmental Protection Agency, because first of all, it failed to estimate the concentrations which it was designed for. And secondly, the assumption of the model, it was assumed that there was a temperature inversion which prevents vertical mixing. However, the design of their model implied that it was really thick and then there was going to be vertical mixing, thus going against the governing equations. Nevertheless, the box model has come handy when analyzing total smoke loading in a valley. And then it can be made better by increasing the height between the source stem and the mixing height. Secondly, we'll be looking at Gaussian plume models. Unlike the box model, which specifies the emission source at the bottom of the box and then assumes it spreads uniformly and instantly, Gaussian plume models specify the emission source as a point or a narrow region containing the fire. If we can see from this image, so we have, this is the emission source stem. So it's just a very narrow point. And then concentrations crosswind of the plume, that's concentrations across these plumes, are assumed to disperse in a Gaussian pattern. This model accounts for plume rise, which is given by delta H. And then, in fact, plume rise is calculated using Briggs equations. In general, Briggs equations have been applied in smoke modeling because it accounts for temperature inversion. Atmospheric transport and dispersion is considered in great detail in plume models. In fact, the transport of smoke is determined by trajectory winds, which are assumed to be constant. And as such, the plume model improves on the box model and leads us to a more realistic model for predicting concentrations of particulate matter. Plume models are advantageous because they do not require so much weather information, but they are, however, limited by the assumption that smoke moves in a straight line under steady states. Because of how random fire is and coupled with complex trajectories as well as the effect of wind, this assumption might not be justified. And then whatever solution, whatever concentration that will be estimated at that point will be invalid. Also, when meteorological conditions change, plume models do not detect altering trajectories or the corresponding concentrations that follow. They've been applied to the simple approach smoke estimation model, which is a screening tool that was designed to assess air quality from prescribed fires in a federal land. The model was also used to estimate ground level concentrations using the emission estimates gotten from the various fuel types. It was also used to calculate how far from the fire the concentrations were going to occur. So this is just Briggs equation, which I stated, and the plume rise together with the plume rise is used together with the plume center line to calculate the dispersion of smoke. So these are just the parameters from Briggs equation. There's like a lot of them here. Then the third model we'll look at is puff models. These models simulate smoke dispersion by creating a sequence of puffs which are emitted at equally spaced intervals throughout the burn. The trajectories are advected through, the puffs are advected through the central location of their trajectories, and they grow with time until they surpass the size of the meteorological grid before they then break apart, forming multiple new puffs. And then each puff contains the volume of the smoke effluent that is being estimated at the time. Unlike Gaussian plume models, puff models have winds that are highly varying in space and time, and as a result are applied in smoke management because they can account for complex terrains where meteorological conditions change and then trajectory patterns are influenced, which, as we saw, plume models cannot account for. Generally, puff models address time-varying variables, thus allowing us to be able to account for the various stages of the burn, such as the burn time. However, the model fails to adequately characterize the source stem, and thus it cannot adequately calculate plume rise. There are several examples of puff models like CalPuff, NSAP+, as well as NSF puff. And then CalPuff is really a model that's composed of three parts: CalPuff, CalPost, and CalMet. So it simulates dispersion using the outputs of CalMet. However, when it was applied to simulate smoke from a prescribed burn, CalPuff was disadvantaged because several activities regarding burns are undocumented. Activities such as the type of fuel that is being burned, whether it's sagebrush or wood or just litter, as well as the time of the burn and the length of the burn. Some of these things are undocumented, so researchers often have to make assumptions, thus introducing errors into their work. Fourthly, we'll be looking at particle models. This model simply predicts the variations of a fixed number of particles as they are vectored throughout the model domain by the mean wind and distributed by the turbulent component, which is added at each step of the equation. So this turbulent component that is added helps the model to account for diffusion. Particle models are commonly referred to as Lagrangian models because they employ coordinate systems that effectively track particles as they travel through space and time. Thus, they assume that trajectory winds are not constant, and so the dispersions vary greatly. Common examples of particle models are high split and flex spat. High split is the hybrid single particle Lagrangian integrated trajectory model. So it's designed as a combined effort of NOAA and the Australian Bureau for Meteorological Research. It's a hybrid model that is widely used to calculate trajectories as well as the chemical transformations, dispersion, deposition, as well as the dynamics of air pollutants in the atmosphere. High split employs a technique involving puffs and particles or both, though maximum emission rate, which is computed by simulating a prescribed burn over a geographical location, is implemented as a constant emission rate in high split. And then plume rise is calculated using Brooks' equation under the assumption that the air parcels rise is based on buoyancy. And then it also takes into account the frictional velocity, the wind velocity, as well as the amount of heat that is being released into the atmosphere. Flex spat, on the other hand, simulates the transport and dispersion of passive tracers in the planetary boundary layer. While most particle models assume that the density in the planetary boundary layer is homogeneous, this assumption might hold when we're in a shallow boundary layer. However, as we go higher in the planetary boundary layer, the density at the top is often lower than that on the ground by at least 20%. And that's because density decreases with height. Flex spat overcomes this by including a density correction term in the equation used to describe the position as well as velocity of the particle. Thus, flex spat can account for variations in density, and it's used in the occasion of inhomogeneous turbulence. And flex spat only incurs very little computational costs. The last kind of smoke models we'll be looking at are Eulerian models. They're used to calculate the transport and dispersion of smoke pollutants using coordinates that are fixed in space. And while it is difficult for Eulerian models to calculate the impact of individual plumes, they allow for a more straightforward evaluation of the cumulative consequences of several plumes. They are often referred to as chemical transport models because they evaluate the effect of chemical changes that may occur when effluents mix with one another and within the atmosphere. One example of Eulerian models is CMAQ, that's the Community Multi-Scale Air Quality Model. It is used to simulate dispersion as well as deposition of hazardous pollutants, as well as the dynamics of pollutants such as particulate matter and ozone. It has often been used to educate key stakeholders about the potential consequences of emissions, as well as produce daily air quality forecasts. However, because CMAQ depends on estimates from fire and non-fire sources, it has inherent biases. These biases have affected most estimates that CMAQ has been used to generate. For example, it was used to simulate particulate matter from the 2007 Atlanta wildfire in Atlanta. And while it's correlated with the observations that occurred after 8 p.m., most of the observations that occurred in the afternoon were underestimated to a large extent by CMAQ. And then some researchers have tried to bias correct CMAQ using the constant air quality model performance, and then combine it using data fusion with satellite as well as observed data to get better estimates. Then another Eulerian model is ASH3D. It's a three-dimensional Eulerian advection and dispersion model that uses finite volume to calculate the concentration of tephra, that is ash particles, at every point in the domain. Using ASH3D, one can solve for mass conservation in the atmosphere. ASH3D is intended for operational settings because it includes very accurate numerical methods. And out of all the papers that we checked, ASH3D was the only paper that included a differential equation for calculating the source stem, which I described is very important in smoke modeling. So this equation here, ds over dz, is the equation for the source stem, where h is the plume height, s is the erupted mass at a given time, and z is the vertical height. The mass distribution over height is controlled by k. So when the values of k are small, there's an even distribution of tephra particles. And when the values of k are large, much of the particles are concentrated at the top. One disadvantage of Eulerian grid models is they are constrained by the size of the grid. However, reducing the spaces can make the models better. Looking at all of the smoke models, we've seen that it is difficult to characterize the source stem. And so these models only scratch the surface of the complexity of the smoke modeling problem, because they rely on emission estimates as well as meteorological forecasts that have wide error margins. There's also the poor capture of plume size and location, as well as weather-imposed constraints. Also, some models are unable to adequately capture the fire size from aerial measurements and discrepancies in the temporal resolution of the data. Because of this, we need a framework that can incorporate comprehensive tools such as the fuel type, the emissions, and all of those to be able to handle various aspects of smoke. To that end, we'll introduce smoke modeling frameworks like BlueSky and the National Air Quality Forecast Capability System. So BlueSky is a framework that is used to model and predict the impact of smoke from wildland fires. Particularly, it has been used to simulate PM2.5 concentrations. So BlueSky combines smoke transport and dispersion model with off-the-shelf weather information, as well as information about the fuels, total fuel consumption, time rate, plume rise, as well as emissions. It estimates PM2.5 impacts from a single fire, as well as the cumulative effects by analyzing information from various sources. And because previous versions of BlueSky had the propensity to overestimate PM2.5 concentrations, Strand et al. Evaluated BlueSky's predictions using observations from the 2007 Southern California and the 2008 Northern California fires. So this is BlueSky's framework showing the various pathways. So the various components are fire information, fuels, total consumption, the time rate, emissions, plume rise, dispersion, as well as meteorology. So several models have been used as dispersion models in BlueSky. We can see CalPOF as well as high split have been used, but particularly for Strand et al., they used CMAC, the chemical transport model. The daily fire information was gotten from SmartFire, and then information about the fuel type was gotten from the Fire Classification Characteristics System, FCCS. The evolution of emissions as well as plume rise was gotten from the Fire Emissions Production System. And then plume rise was also gotten using information from Briggs equations, which I mentioned is a very important equation for smoke modeling. The total fire consumption was gotten from the consume tree, which is a simplified version of the Fire Emission Production System. And then meteorological data was gotten from the Penn State Mesoscale Model 5 data set. When the estimations from the Northern California wildfire and that of Southern California fire were compared, it was observed that BlueSky predicted well to a great extent the fire from Northern California fire. And after some point, it started overestimating it. But for the fire from Southern California, BlueSky underestimated it because it was difficult to characterize the source stem at that point. For the Northern California fire, the advantage was the placement of the smoke monitors. So there was the narrow and broad valley where the smoke monitors were placed. However, the smoke monitors that were placed in the broad valley did really well, while the ones placed in the narrow valley underestimated PM2.5 concentrations. Lastly, we'll be looking at the National Air Quality Forecast Capability System. So it's a fire signal capturing algorithm that utilizes several models and observational data sets. It depends on BlueSky, which we just saw for emissions data. It depends on the hazard mapping system for the fire detection. And then it employs smoke to calculate plume rise. So this time around, it depends on smoke and not Briggs equations for plume rise. And it depends on Hello?
Yeah,
We can hear you now.
Yeah, we can hear you.
Yeah, you're back.
Oh, I think my network went off. Okay, let me share screen again. Can everyone see my screen? Hello?
Yeah, we can see it.
Yep.
Okay, where did I cut you guys off?
We are getting
Yeah.
you, Patricia.
Yeah, I think right on that slide.
Yeah.
Okay,
The NEQFC.
I think you were talking about NOAA.
No. Oh, I think it was BlueSky. Was it BlueSky? I don't know.
Yeah, I think the same
Did
slide
you
you're
guys
sharing
get
now.
the BlueSky? This one?
Yeah, we got the
Okay.
BlueSky, yeah. Just the smoke
Okay,
modeling framework.
so I was saying the National Air Quality Forecasting Capability is a fire signal capturing algorithm that makes use of multiple observational sets as well as multiple models. So it depends on BlueSky, which we previously saw for emissions data, and then it depends on the hazard mapping system to detect fire spots. It also employs the sparse matrix operator kernel emissions, that's smoke, to calculate plume rise. So this time it doesn't depend on Briggs equation. And then it incorporates CMAC as the chemical transport model for dispersions because it tries to check some of the chemical components apart from particulate matter, such as carbon monoxide, as well as potassium. And then the multi-scale model is what it uses for its meteorological forecast. The fire capturing capabilities of the NAQFC system is very essential in smoke modeling because it forms the very basis of the smoke modeling. At the very least, it helps to identify the location of wildfires and analyze their magnitude as well as the time and duration of the burn. However, it is difficult for the NAQFC framework to adequately describe emissions as well as their impact on air quality. This is because the framework is limited by cloud cover. And another setting of those framework is that when a fire spot does not have smoke, it is omitted, thus reducing the number of data sets it uses. Also, because there's so many observations and models, the temporal resolutions are different on a constant emission rate, as well as CMAC, which has biases, because CMAC is not bias corrected in this case. So it introduces errors as the whole process is going on. Now, going through all of the models, we see that there are several models that we can use to simulate smoke transport. However, not all of these models are effective. Then the chief challenge of this model is because it is really difficult to characterize the emission source stem. There are so many assumptions that researchers have to use, which lead to oversimplification, the reliance on fire estimates, which themselves have errors, as well as the location of smoke monitors. And then while it is important to develop new modeling approaches, it is also important for researchers to delve deeper into the findings of others. Instead of maybe building multiple models, it is possible for us to look, for example, into the source stem that was given by the ASH 3D model to check how it can be incorporated into smoke models. Also, some models lack some fundamental physics to make for more realistic models such as the box model, which do not account for plume rise and diffusion, which are key parts of the underlying physics governing smoke. Instead of leaving these models as standalone, it's possible to incorporate them into another model. For example, we can incorporate the box model to serve as the emission source model inside another model. And then large domains and time scales put a strain on computational resources because not all locations on the domain have smoke. So instead of using, it's very essential to implement adaptive mesh refinement so that it only targets locations that have smoke on the domain. And then it's also good for us to look into the sensitivity analysis of these models and see which parameters affect the concentration as well as the simulation of smoke in general. And also we also noticed that getting smoke data is really difficult because some things are undocumented and some other data requires like security access. So it will be much easier if data is freely available. These are some of my references. Thank you.
Yeah, thank you, Patricia, for this wonderful presentation. So at this moment in time, we're going to take in questions and feedbacks for Patricia. So if you have a question, just unmute and go ahead and ask.
I think, did your slides not advance?
Huh?
I think we're still looking at you had said something about references, but we're still looking at your slide number 17.
Whoa, it's on page 20 here. What's happening?
We are still on 17.
Okay, let me stop sharing. Hello?
You stopped sharing?
Yeah, so I would like to talk about my computing artifact.
Just a minute. It looks like you're still sharing here. I don't know. Maybe try.
I don't know what's wrong with my network today.
Maybe try to log in and out.
Okay,
It's a good idea.
That. Can you guys hear me?
Yeah, we can hear you.
Okay, I thought I started a screen sharing, but I can see it. So should I go on to present my artifact, or will the questions come first?
Oh,
you're muted.
Oh, sorry. Maybe you can just proceed, show us the brief about the artifact, and then people proceed with the questions afterwards.
Yeah,
maybe
go
just
ahead.
2 minutes, yeah.
Yeah.
Okay. Can you guys see this?
Yep.
Okay. So in this notebook, we'll be simulating PM 2.5 concentrations using Smoke 3D. we'll be simulating concentrations, PM 2.5 concentrations in California using the Smoke 3D solver. So this solver is implemented in Forest Claw. You can check that on GitHub. So Forest Claw is a suite for solving hyperbolic partial differential equations, and it makes use of adaptive mesh refinements, which I talked about previously. So it targets only regions with smoke on large domains. So this software is really computationally cost effective. So in order to run this notebook, it is assumed that whoever is running it already has Forest Claw and Smoke 3D installed. When you go through the GitHub wiki for Forest Claw, you can see how to download Forest Claw. So in order to be able to run, so this Python script helps us, this is like a front end that helps us to run Forest Claw as a black box. So it simply helps us to run what would normally run on the terminal. And to do that, we have to import some modules that help us to imitate the functionality of the Unix shell. So the modules are the subprocess, Schlex, and the OS. With these modules, we can be able to connect to the input files in the folders we have them and then return the outputs of their code. So we simply just import them here and then we set up the problem for the source stem. And we want to get a source model that is realistic. So before we do that, we consider the advective transport equation, which is given here. Is this clear enough? So the right-hand side is the source stem, and Q is the...
Patricia, I think your slides are not moving. Yeah? The notebook is not scrolling up and down. It's still at the same position.
Oh my goodness. What do you see now?
We can still just see the first top part of your notebook.
I think I have an issue with my network because
yeah,
I can see it's doing a different thing from what you guys are saying.
Yeah, I think maybe we can just proceed to the questions. I guess so.
Okay.
Yeah. So if anyone has a question.
Maybe I should go back to the other one. I'm really sorry, guys.
Yeah, so if anyone has a question, you can just try to unmute and ask Patricia.
Hey, Patricia, can you hear me?
Yeah.
Yeah. So question for you. So how do, I guess, so these solvers that you were talking about for simulating the ash and stuff, do they incorporate like climate data or weather data for how, how the wind is moving and things like that?
Yeah, some of those like models incorporate that. Like I talked about the Penn State National Center for Atmospheric Research, the mesoscale model 5. So that's meteorological data. So it includes like wind data and all of that.
Got it. Okay, cool. Thank you.
Bye.
Yeah, Patricia, I think I also have a question for you. Actually, two questions.
Okay, I'm listening.
Yeah, you talked about the plume model improving the box model. How is it done? As in, how is it improving the box model?
Okay, I mentioned that it improves on the box model by accounting for plume rise. The box model does not account for plume rise. So the Gaussian plume model leads us to a more realistic model for estimating smoke because it actually includes plume rise, which is a very useful physics and smoke model.
Okay, maybe another last question is, so you stated about the BlueSky having most of the feature that these other models are not having. It's like it's incorporating most of the features. So the BlueSky is the model which is performing well at the moment for predicting smoke.
I can't hear you catching that.
Did you get my question? Let me.
Kachiga?
Yeah, did you get my question? I don't know if you got my question.
No, I didn't get you. It trailed off at the end. You said it incorporates other models or something.
Yeah, I said the BlueSky is like it's incorporating most of the features as compared to this other model. So my question is the BlueSky the most performing model, which is outperforming these other models in predicting the smoke transport?
Well, so far, even though BlueSky incorporates some other models, it still is not perfect, which is why several models are still on their way to see which one does better. And then also because researchers often want, maybe what they want is different from what another person wants. For example, like the NAQFC system is really detecting fire spots, while BlueSky is estimating concentration. So what BlueSky is doing somehow is different from what the other one is doing. But still, BlueSky, like I mentioned, it underestimated concentrations from the Southern California fire. And then while it did well for the Northern California fire, at some point it started overestimating. So which is still a problem that is trying to be solved.
Okay, thank you.
All right.
Yeah, so I think I have a question.
Okay.
So you did mention about this, if I'm right, is it narrow and wide valley in Northern California or something like that? And
yes.
then one of the valleys, like you were able to, it captured the smoke data like quite well. And then in the other valley, I think in the narrow valley, it didn't. So I was wondering if the location plays a role, or like what might be the reason for that.
Yeah, so for the Southern California fire, generally, its advantage was the location of the smoke monitors. While it performed well, but still the ones in the narrow valley did not do so well.
Okay, so, and that's just mainly because of the location?
Yeah, the location had an influence on it.
Okay. So I think you also mentioned this thing about satellite and observed data. So I was a bit confused as to whether satellite data is not observed.
Say that again.
I think at the point you were saying something about satellite and observed data. So I was quite, I don't know, like it looks like satellite data observations, right? So I don't know if there is a difference to that.
Okay, maybe I didn't put it well, but the thing is, some are taken using satellites, like aerial measurements from the top, and then some are using like smoke monitors that are placed on the ground.
Okay.
Do you get it now?
Yeah, I get it. That's it for me.
Oh, okay.
Yeah, maybe just to add up the question Titus asked about the calibration. So when you're calibrating, do you have to calibrate based on each location, or how is it done, or just have to pick the certain parameters that this will work for this region for the models?
Maybe you should rephrase your question. I don't understand.
As in, since Titus asked about the model performing badly on a certain location and the another location is performing better. So when you're calibrating this model, do you have to pick certain parameters for this location, or as in, do you have to pick certain parameters basing on the location?
I think what the researchers did was they just estimated the concentrations for that location using observed. And then they noted, yes, using observed concentrations that were already established. And then they noted that because of the placement of the monitors in the different valleys, the model either did well or did not do so well.
Okay, thank you.
Does that answer that?
Yeah. Yeah, so
Just a final
okay.
question. Yeah, so I think there was one of the models you mentioned that incorporates differential equations, right? But
Okay,
I quite
the
didn't.
Ash 3D model that
Yeah,
uses differential equations for the source term.
yeah, but I think I quite didn't get how, I don't know, like how that what the advantage that the using differential equation gives this model.
Okay, so basically what I was saying was, of all the papers we looked at, we wanted to see which of them actually included the equation for calculating the source term. And while some of them just simply used concentration emission estimates from other models, this particular model wrote the equation that was used for the source term in order to get the concentration of tephra particles. So we're able to actually see the equations that were being used in order to understand what was happening, while the other papers did not include, they just tried to describe what they did. Hello, Titus.
Yeah, I think I get you. Yeah, so the other people just described what they did. So
Yes,
does it mean they use the differential equations, but they didn't write them down, or they didn't use differential equations at all?
some of them actually stated that they used estimates from other models. So they just said they used estimates from other models.
Oh, okay. Yeah, I think that's it. I just wanted to know what advantage the differential equation brings into the modeling.
Okay.
I think people have exhausted their questions at the moment. So Patricia, thank you so much for this wonderful presentation which you've given to us. We wish you the best. Is it next week?
Yes, next Monday.
Yeah, so just make sure that you send us the location. Is it on Zoom, online, or
It's on
remote?
Zoom.
It's on Zoom. Okay, yeah. Just make sure that you send the location or the link. Yeah. Thank you so much and wish you the best. And just an announcement. Yeah, we'll be sending an invitation we'll be hosting a party at Morrison Parks, like come together just to have some discussion about SIAM and everything, which we've been going through. And yeah, just to share the experiences. Yeah, we'll be sending an invitation for that.
Okay.
Yeah. So I don't know if there's another announcements, Bran. Yeah.
Yeah, so yeah, we'll be presenting on October 12th to take us through what he did over the summer. Yeah. I think that's the announcement.
Brian, but I think there's another week before October 12th, right? So like next week, who presents?
Yeah, that's where we're gonna have a get together. Yes, a social event.
Yeah.
Oh, sure. Okay.
Yeah. Next week.
Yeah, so thank you all for coming. Have a blessed week and enjoy the rest of the week. Thank you.
Yeah, bye.
Thanks, Patricia.
Thanks, bye.